yesterday we were learning about stacks, but we haven't actually talked about how to implement anything about a stack yet. All we did was talk about what we can do with the stack. And we like our stacks, like when we design things like this, we like to talk about them in this abstract sense where how they do what they do isn't as important as what I can do with them. And if we assume that the what is implemented, however it's implemented, if we assume that it works magically, then what can we do with it? That's what we want to play around with. So let's pick up from last time. So, we were talking about some of the things that we want our stack to do. Well, we want to be able to add things. This is our push. Pop is remove, and peek is similar to pop, but it doesn't actually take anything out of the stack. It gives us a pointer to the thing on the top so we can look at it, but it stays there. And why not have something like a toString, check if it's empty and what the current size of the stack is. I mean, we could add extra things, I guess, as long as we don't break the property of the stack of all the action happens at the top, all at one end. And I know I said this last time, but everyone every year will ask, why, but we can code it so you can get the second thing in the stack or the third thing. And you're right, but then that's not a stack. We're breaking the rules of what a stack is. So it's just a bunch of operators. We haven't said how we do anything, which is what we want. It says nothing about where we're storing the data, how the operators do what they do. We don't know. And this has nothing to do with C++ or any other programming language. So the stack abstract data type it's a collection of data, and the operators we can use on the collection of the data. So that's what we saw here. So this is the definition of the ADT. This. Loosely. So things that we can use a stack for. I'll warn you, this isn't the greatest example in the world. We'll do a better example later, but we like infix. 3 plus 4 times 2 is 11, or I guess parenthesis 3 plus 4 times 2 is 14. And computers like postfix, which is this weird thing, which in this case it would be 4 times 2, and then the result of that plus 3. Or this is the 3 and 4 added together, and then the result and 2 are multiplied together. And here's a very simple algorithm that will take a string that we'll call expression and start parsing that string one character at a time. And if we use a stack, and again, you'll notice that we're using it, but we do not have any implementation yet. But by using the stack, we can solve this problem. So for each symbol in the expression, if the symbol is an operand, something like a number, we're going to push it onto the stack. If it's an operator, we pop 2 things off the stack, apply the operator, and push the result, which will be an operand, back on the stack. Can you go back? Didn't get that down. Slides are on Moodle. Slides are on site too. Yeah. But here, don't worry too much about this example. We'll do a better example after we go over this one. And here is an example expression here. 7, 4, negative 3, multiplied 1, 5, plus divided by multiplication. Well, let's see what happens. We see a 7, and if we go back to the thing, it's like for each symbol in the expression, if it's an operand, push. If it's an operator, pop twice, apply the operator, and then put the result back on the stack. So we see a 7, push. See a 4, push. Negative 3, push. So the top is currently negative 3. But then we see the multiplication. So what do? Well, take off the negative 3 and the 4 and apply the operator, which is multiplication, and then put the result on the stack. So that's why we end up with negative 12. Then we see a 1, okay, push the 1. We see a 5, push the 5. Then we see plus. So we should pop off 5 and 1, add them together, and put the result on the stack. So 5 plus 1, and then 6 goes on the stack. Then we see divide. Okay, we'll take 6 and negative 12, apply the operator. I guess this is how I defined the order to happen, but I guess it really would matter if we were doing negative 12 divided by 6 or 6 divided by negative 12. But let's assume it's this order. So we get the result, it's negative 2. We see another operator, the multiplication. Well, pop 2 things, 7 times negative 2, and put it back on the stack. And you'll notice that after the whole expression is being done, after it's done being evaluated, it's we have the total, like the final result there. And did I remember to start recording this lecture? Yes, I did. Okay, good. All right, so the implementation. Actually, before the implementation, let's do a better example. Postfix is perhaps too complicated for the sake of being complicated. Let's say we have something, like we have an expression that's something like 5 plus 2 minus 7 divided by, and we got a squiggly bracket. I'm just switching types of brackets here. 14 minus 1. Let's just, is there an easy way to delete this? Okay, I'll just turn this into one big close parenthesis. Okay, great. So a really simple thing, like whenever we're looking at this, we want to make sure that the brackets line up, right? For every open, there's a close. And this would work similarly regardless if I use different brackets or not. So 5 plus 2 minus 7. I guess the shape of the brackets don't really matter too much. 14 minus 1. Okay, so there's like a simple expression. Okay, we can use a stack to see if the opens and close match. Because you'll notice, like, even when you're programming, right? If you forget to close a bracket, it's going to get mad at you. If you forget to close your squiggles, it's going to say, like, oh, we've got an issue. So in this example, how can we use a stack? Well, if we see something like this, we push, our stack starts like this. We see an open, so then it transitions to, and I'm just going to represent these as like circles. We've got an open. Then we see, okay, whatever, ignore. Now we see another one. Okay, so that will now transition to, we've got 2 opens. Then we go over. Oh, we see a close. So when we see a close, we'll pop from the stack. And if we pop from the stack, and we can do it, we're in great shape. So we're now here. We can just pop one of the opens off. So you'll see that like it kind of keeps track, like the top is the last bracket that was opened. Divide, open, okay, so now we've got that open there, and then we go along, we see this close, and I'll just carry on down here. So we pop one of them off the stack and we're good to go. And then we see another close and we pop the other one off the stack. And now it's empty, so we know we're in great shape. But you can imagine that if I had like an extra open here, we would be left with this last one on the stack, which is no good. And that would tell us that, well, we actually have a hanging open. Or if we had an extra close here and we tried to do this, we tried to close, but the stack's empty, and we're looking for, well, where's the open that goes with this close bracket? We're in trouble. Just gonna clear all this. Now don't get too bogged down by this example. This is just an example. Stack Overflow. That's gonna come up different, but the stack in Stack Overflow does refer to the idea of a stack. All right, implementing a stack. Well, we saw how we can interface with it, the abstract idea, but how, like, so we know how to use it. We can push, pop, whatever. But okay, I know I was all talking about abstraction. We still got to know how the hell we implement this thing. So we haven't talked about how it works. Well, now we need to implement. Okay, so implementation details. We need to think of a thing that's going to hold on to the data for us. And if I were to ask you right now, based on what we've seen in the class so far, what is a handy tool we have in our tool belt to hold on to information? Well, chances are an array would probably do the trick. And I'm betting a lot of you were thinking like, well, I know arrays. Yeah, okay, perfect. We've got an array. We can put information in an array. It's like a collection of information. We're happy. And we also need to keep track of the top of the stack. Because if we have this array, we need to know where we're adding things or removing things from, pushing and popping from. And we also might want like something to keep track of how many things are on the stack or in the stack. I don't know how we'd want to say this. I mean, we could add a couple of other attributes if we really want, but this is probably pretty good. This is sufficient at a high level idea. So we're going to make a stack with an array that's going to hold integers. Why ints? Well, we're going to start with this specific example. Actually, technically, we're going to have pointers to integers because remember, I love pointers. What do we see here? Do operations on the stack always do second in stack here? Then what? I'm not sure. Second.
Like for like when you had the stack was 6, negative 12, 7, and you divided it, we got -2, not -1/2.
Mm-hmm.
Does it always do the second?
No, don't. That doesn't matter. That you're thinking too hard. That's a specific example of just the idea of using a stack. That has nothing to do with how we're implementing it. So don't worry about it. That would be like, okay, we pop from the stack. Because that algorithm's using the stack. We are building the stack. So how they use the stack in the order that they got the things from the stack that's up to the coder of the algorithm, but not the data structure that we're going to write the stack. So that question you're asking, interesting question, but not relevant to the development of our stacks. Yeah, so we're going to have an ArrayIntStack, and it's actually going to be an ArrayIntPointer stack, but whatever, we'll call it an ArrayIntStack. And here's the idea I want. So I've got some stack called S, and over here, like, I mean, this is an arbitrary name, S, but like maybe in our main, we create a stack, something like S stack S equals new stack or something, right? Like that's what this is. But then the idea is, okay, within this, we've got this like, okay, object, and within it we have something called like the stack, which is going to be a pointer to an array that's going to be full of pointers to things, which in our case are going to be numbers like 1, 2, 3, 4, for example. And we're going to have to know the top. Where's the top of the stack? So, well, the top is going to be here. And you might say,
no, other way.
Why,
This way?
like, you know, for...
On top?
Well, someone's mic is on. You might want to mute yourself, whoever you are.
Whoa! Whoa! How do you do that? Okay, wait.
If you don't... Who is that? Let's have a look.
It's a bit small of a...
Wait, how do you do that?
Madeline.
Just put your phone on, yeah. Yeah. Please, yeah.
Sounds interesting, yeah. I'm going to mute her temporarily just because... Okay. Yeah. All right. So you might say, well, the top, you know, it's the next available spot. Yeah, that's what we're going to do. And this has the advantage of like, well, it plays double duty because top is like, also tells us how many things are in here because there's like 1, 2, 3, 4 things. But 4 is also the index of the next available spot. So top really, I guess, in the array implementation isn't where the top is, it's actually where the next available spot is. So if we want to get access to this, it'll be top -1 because, well, that would be 4, -1 is 3, so index 3 has the last thing. So just remember that it's the same idea with the country catalog and the course objects we were building before. So if I come along and I push a new element, I want it to look like this. And then the top would become 5. If I pop an element, well, okay, so now top is now 4 and this thing's not there anymore. And if we pop a second element, this is what we would end up with. And I guess the things in 3 and 4, like they're gone. They're not in the stack anymore. Okay, an ArrayIntStack. So stack will be an array. The attribute stack will be an array that we're keeping the integer pointers in. And top will keep track of where the top is. Asterisk, and remember this is conveniently of how many things are in there in zero-based indexing, and really it's the next space, not really the top, but for our purposes we're going to call it top still. And what else do we probably want? Well, maybe max to keep track of how big the array is, because you might remember from the course example or the country catalog example, we need that expand capacity thing, right? Because if I make an array of size 10 and I want to start adding 100 or 11 integers, well, I'm going to run out of space. So we need to be able to just automatically have a bigger array. So let's start by creating our header. So what do we see? Well, okay, so class ArrayIntStack open, and then the private attributes, max, top, and then an int pointer called stack. So this is going to be like an array of pointers to integers. And we're going to have our constructors and deconstructors. So our default one that takes a size, so it initializes our array of a specific size. Then a copy constructor, because we want those typically, and then a deconstructor. We're going to need to tell C++ how on earth it's to delete a stack if we ever want to delete a stack. We're going to want to push. We're going to need our expand capacity, because push, we might run out of room. We're going to want to pop. This is going to return an integer pointer, the thing that was at the top, and also remove the thing from the stack. And peek, which leaves the thing on the stack, but still returns a pointer to the thing at the top. And then also perhaps size and is empty and like a toString. Okay? So this I think is pretty good for what we're going to want for our stack. And you know what I'm going to do? I'm going to start copying this code over to here, and I guess I need to add. So I've got my project here. Add a new class, ArrayIntStack. Okay, and then there. I just copy and pasted the header over from the slide. So we're going to need to implement all these things. Probably good to start with the constructors. So you'll notice that the constructor here is going to look an awful lot like the course in the country catalog. We're going to start by saying, I don't know, max is 10. Why? I don't know. I made this up. Where's the current top of the stack? Well, it's empty, so the top is 0. And then stack, well, we need to initialize our new integer pointer array. Okay, so let's go to our int array stack here. Nope. ArrayIntStack. ArrayIntStack. We'll do our default. So we'll do max equals 10. Top equals 0. And equals new int star array of size, whatever the max is set at. You may remember that in the example we did with the course, that we actually made, like, we had another attribute in here that was a constant that kind of had like the default max capacity. We could do that here, but I'm a little lazy and I'm just saying, like, whatever, just set it here. It doesn't need to be set as a constant. So there, we're all set. Now, I want to re-emphasize that what we're really going to have here is the stack. So like stack is a variable that contains a pointer to an array that contains pointers to integers. Okay, that's what we have here. It's not an array of integers. It's an array of pointers to integers. That's why we have the 2 stars here. The first integer star is kind of like saying, well, okay, it's a pointer, and when we created it, it was an array. So the fact that like it's an array, that's one of the stars. And then the second star is the fact that it's full of integer pointers. So there, we're all set here. Oh, and also notice that in this previous example, where was it? No, I went way too far back. My goodness, how far did I go? There. This here is the example of what I was drawing. An ArrayIntStack object in this case would be like the S. Okay. Yeah. All right. So we've got our default constructor, and then let's have a not default constructor, which is just, it's going to be the exact same thing. Because it's not the exact. It's going to be almost the exact same thing. The only thing is, I guess, we're passing the size, and then we set the size to max. So let's take this and int size, and we're good to go. Cool. Looks pretty good so far. Yeah. So now if we want to create one, well, this is what we would do. We would say ArrayIntStack pointer, because remember, I like pointers, so you're gonna like pointers too. ArrayIntStack pointer, S, is equal to a new ArrayIntStack 5. So what this will do is set max to 5, top to 0, and this is what we've got. And of course the array is initialized with just garbage in there. So this is what we would have if I run this code. This would go get created in our computer somewhere. And S would be a pointer to an array stack, so that's what this variable is here. Now, let's write our copy constructor. How are we going to want to do this? And you might remember, it's the same question we were asking before. How deep do we want this copy to be? Do we want to make it so like, okay, well, obviously we're going to want to copy over like the max and the top. That's obvious. But when we copy over the array, like the contents of that array, what do we want in there? Do we want to make like a full copy of that array, or do we just want to copy the pointer over and have it point to the same array? Now, the way I've implemented it here, it looks like we're doing the deep version here. What are we doing? Well, actually, it doesn't even look like we're doing that deep of a version. What are we doing here? We're making a new array. So assuming that we have an array somewhere in RAM that is holding on to the information, we're making a copy of this array. So this one stack is equal to the size of whatever the old one ultimately was. 1, 2, 3, 4, 5. So we're making a copy of the array, but we're like, what are we doing here? So for the top, so from 0 to the top, we want to copy the contents over. But when I say this, the way this is written, I'm actually not making a copy of the contents. Pardon me, I'm not making a copy of the thing. So this has a pointer to a number 1, for example. This has a pointer to a number 2. And this has a pointer to a number 3, okay? So I've made a copy of the array. That's this one here. This is the copy. But here, I'm just straight up copying the contents of whatever's in the original stack's index I, which is a pointer to this one single integer. So I'm actually, although I've made a copy of the array, I actually have, the way this is coded, I have coded it such that this is not as deep of a copy as it could be. We're not making copies of these integers. We are using the exact same one integer that's created in RAM, and we have 2 pointers to it. You might ask why? Well, why not? Why did I not make this as deep as a copy as I could have? I don't know. I guess I didn't want to in this particular case. And I guess it kind of makes sense, but we don't need to think too much about that at this stage. The point is, this isn't a deep copy. In order to make this a deep copy, we'd have to make a copy of all of these integers that the array had pointers to. So let's copy this code over. Okay, so now we've got our copy constructor, and then we will come back to our deconstructor a little later. So here's a really simple one. Get the size of the stack. All right, well, just return whatever the top is, because the top just so happens to have the number of things in the stack. Let's put that the way it was, just for consistency purposes. And then I guess the isEmpty is going to be relatively simple as well. It's just basically asking, well, if top is 0, return. If top is 0, that's true. And if top is 0, that means that there's nothing in the stack. So if top is 0, then this is true, we return true. If top isn't 0, that means there is stuff in the stack, so this function returns false. Okay? And toString. All right, I'm just going to copy this on over, and we'll talk about it. So what do we got here? Well, okay, remember this is returning a string. And remember, our toStrings return strings. They do not print out strings. The string being returned, whoever called this function, this method, they're the ones that are up to, like, they get to decide what they do with that string. In our case, we're just returning the string. We don't print it out. So what are we going to do? Well, I'm going to start with an empty string, just an immediate open and close quotes. This is a way to create a string, but there's nothing in it. And we're going to do string building. So for I, from 0 to whatever top is, take S and append to S the string version of the integer at that index. And we need to dereference it because the thing at stack at location I is actually a pointer to an integer. So we need to say, no, not the pointer, the actual integer. Turn that integer into a string, append it to the current string, and add a comma and a space. And keep doing that. And at the end, we will also add this extra little thing here that's like top. Then we return the string. And top is just to signify which end that we're looking at is the actual top. I'm getting fancy here by adding this top thing. It's completely unnecessary. You can do this however you want. If you wanted to do this such that they went on new lines, cool, whatever. I did this all as if they're all in one big line. Okay. Okay, yeah. Okay. Push. So how are we going to add something to the stack? Well, first, it's a simple idea at first. Well, go to the stack at top, at index top. Because remember, top is the next available spot. Then we're just going to take the thing that we're actually trying to push onto the stack, which is a pointer to an integer. So just put that pointer in top and then increase top. That's it. Simple. But of course, you remember from the course object and the country catalog from assignment 1, we might need expand capacity. If the top happens to be equal to the max, that means our array is full. There's no more room in our array. And if that's ever the case, we got to call expand capacity. So if we're out of room, expand capacity, and then carry on as if everything's normal. If top isn't max, well, we skip this, and then we just do the simple idea of adding something to the stack. Just put something in the array in the next available spot, and then increase where the next available spot is. Of course, we're going to have to write expand capacity, and it's going to look exactly the same, basically, as we had before. Copy constructor. Okay. So this looks pretty good to me, except of course we have to write our expand capacity. So we can start that. Nope. So expand capacity. Yep. It's not going to take anything. And it's not going to return anything. It's just going to double the size of our array. We have to manage our information as well, because we created arrays in dynamic memory, so we're going to have to delete the old array. But let's go back to the slides and look at what we got. Expand capacity. So it's always good practice to double the size. If our size was 10, well, the new one, make it size 20. And later on in the course, we'll talk a little bit about why doubling is the right idea. And then what are we going to do? Well, we'll make a brand new array of integer pointers of the size of whatever the new max is. So if it was 10, well, now it's 20, and then create size 20. Copy everything over. Remember also that we can get away with the fact that we're copying, like we absolutely are happy copying over the pointers to the integers that exist somewhere in memory. We don't want to delete them. We don't want to make copies of those integers because that doesn't really make sense here, because we're getting rid of the array, the original array that holds onto the information, the array that's too small. So we can copy the pointers over to the new objects, and I'll draw this out. Here's the old array. Here's the new array. This has pointers to things. And these, I don't know, I'll draw them as like little circles. Really what I want to copy over is just the pointers to those things. We don't need to make copies of these things in this case, because once we delete this array, which we are going to do right there, this doesn't matter anymore. So we're good to go. So go through the array from 0 to top and copy all the contents over from the stack to the new array, delete the old stack, and then make stack point to the new array. And that's it. So in this case, I had stack originally pointed here, and then we had new array, which pointed here. And then we deleted stack, and then we say stack is new array. So, okay, stack, you don't point there anymore, you point there. And then this variable that is a pointer to this array, I mean, this doesn't matter anymore. It disappears once the functions or the method is done running. As always, though, if I'm going too fast or you have a question about what I'm doing, definitely put something in the chat. I guess I already copied that part over. So now expand capacity should be pretty happy. Double the size, make the new array, copy the contents over to the new array, delete the old array, and make stack be pointing to the new array. Okay, cool. All right. Yeah, okay, cool. Now pop. All right, well this is going to definitely be easier than pushing, because with push we might have to expand capacity. With pop, I mean, there's going to be something there. And I guess if the stack is empty, we have a particular funny edge case. But if it's empty, I guess, like, what are we going to do? We'll come back to this. But assuming it's not empty, what are we going to do? Well, just decrease top and then return the thing at stack top. There, done. Because as soon as we decrease top, I mean, that's the same thing as saying top equals top minus 1, which we're going to want to do. Like, I could do it like something like thing equals stack at top minus 1, then do top equals top minus 1, then return thing. But this is a little like easier. Just decrease top, because we're gonna have to do that anyway. And I mean, the decreased top is going to be the thing that we want to remove. So we're good to go. We don't need, like, if the array is like this, and we had this, and this is the thing we want to remove, is like, if top was 0, 1, 2, 3, 4 before, if we just set it to 3, the next thing we add is going to go in location 3, so it'll overwrite this, so we don't care about setting this pointer to anything. But if you want to be super safe, you could do it this way and then say, like, thing at top, stack, S-T-A-C-K, at top equals that null pointer thing we talked about before, if we want to get super fancy, but it's not necessary. Now, what are we going to do if our stack is empty? What should we do? Let me delete everything here. This is only going to work on Windows with Visual Studio. So if you're on Mac, it won't work as well. What we can do is we can throw an exception. And if you're on Mac or any other platform, you can just say this. Just don't put, the only difference is you don't have to put the string in there. But having the string there is a little bit more descriptive. And what this is saying is, okay, what are we going to do if we try to pop something from a stack that's empty? What do we want to do? Now, we will talk about exceptions a little later, and for those of you that took 161 with me, I know you're familiar with exceptions. But an exception, it's not an error. It might be an error. It might be representing something that's an error, but an exception is something exceptional that happened. Because what do? I'm coding this stack. What do I do if the stack is empty and I try to pop from it? Do I want to just ignore it? Just like, okay, well, there's nothing there to pop, so just do nothing. Return, down here, return null pointer, maybe if it's empty. Or do I want the program to immediately stop running because something super bad has happened? Do I just want to, like, print out to the user, like, oh, something funny happened? I mean, there are a lot of things I could do here if the stack is empty. But here's the thing. When I am writing this stack, I have no way of knowing. So, like, I'm writing the code that defines this data structure, this stack. And depending on how you're using this stack, you might want it to immediately crash, print out an error message, just ignore it and do nothing. But that's up to you, the user of the code I'm writing right now. How can I know today what you need to do if we have this exceptional situation happen where the stack is empty? I don't know what you want to do with it tomorrow when this situation happens. So I'm going to throw an exception, and then whoever uses the pop method, if they see an exception come from this, they get to, like, if they see the exception and it's like, oh, the stack's empty, well, it's there that they can write the code to manage what they want to do. Like, oh, crash immediately, or just ignore it, whatever. So if it's empty, we'll throw this exception. Our peak, it's going to be basically the exact same thing, except we don't actually want to decrease top because we're not removing anything from the stack. Just return the thing, or return a pointer to the thing that's pointed to by the thing at the top of the stack. Ugh. So in this case, just, yeah, return the pointer to the integer that's supposed to be on the stack. So I'm going to go copy these things over. So here's our pop. There's our push. Let's do pop here. And, well, let's not throw an exception twice. And then here, just copy this over. Okay, cool. Whoa. Cool. All right, I hear a question. Boop. Why top -1 here? Well, remember, top is the empty spot. No, so the other one was effectively top -1. This right here, no, wait, I went the wrong way. What? Did I? Pop. Pop. We decreased top before. So it's like right here we said top equals top -1 and then said top. So effectively we did top -1. But in this case, we would also need to make sure we leave top one less than it was before because we removed something from the stack. Where in this case, I don't actually, with peak, I can say top -1, which will give me the number top -1, but it leaves the value of top alone. So in this case, if top was equal to, I don't know, 4, this would make top equal 3 and then return stack at top. And we're good. We're in great shape. But if top is 4, we just return stack at top -1, which is 3. But top still stays as 4. So that's the difference there. Did that answer your question? I'll assume it did, but let me know if it did. And now our deconstructor. How are we going to delete this thing? Well, I know that we're going to want to go through, I mean, based on what we saw with the course and the country catalog, we're going to want to go through our array and delete each thing in the stack, or each thing that the content of the stack points to, right? And then at the end, we're going to want to delete the array stack itself. But hold on a second. Whenever we delete stuff, remember, for every new, we need to delete. But we have to be careful and we have to think about who is responsible for that memory that was allocated. The stack right here, this thing, I am absolutely responsible for this because in my constructor, I said, okay, new stack. Okay. So it makes sense that I'm responsible for it. So if I delete the stack, I can delete the array that's holding on to the information. But you'll notice that this stack never actually created the integers that the array, like the array called stack, pointed to. We never created the integers in here. Let's go back to push, where push is the only thing where we add stuff to it. And you'll see that push, we're going to get an integer pointer. So the integer is already going to exist, and we're going to give a pointer to that integer with our push method. So this stack is not actually responsible for deleting the integers in our stack because someone somewhere else made those integers in order for us to get these pointers to them. So we're actually not going to be responsible in this case for deleting this. All we need is delete this right here. So I'm going to take all this, go up to where I think I should put my deconstructor, which is right here. But of course, like I just said, we do not need this because when we push things, we assume the integer already exists because we're getting a pointer to an integer that exists. And then we are putting a pointer to that existing integer on our stack. So whoever created the new integers that we are now pushing on our stack They're the ones responsible for that data. Now, if it just so happens that the user created a whole bunch of new integers, pushed them onto the stack, and then deleted the stack, but lost reference to the integers, like they lost their pointers to the integers that they added to the stack, and we call delete, well, now we have a memory leak. But that's not the stack's fault. That's the person who used the stack and failed to deallocate the memory that they had dynamically allocated to our integer pointers. Technically, we don't even need to have dynamically allocated integer pointers. We could have integers that were stored somewhere in memory, and then we just get the address of those, or they could be integer pointers to integers that we created in the dynamic memory. If it's the static memory integers, we don't even need the delete on those things. But if it's dynamic memory integers, we sure as hell need those deletes. Now, this is really all we need to do. I mean, we could add a little more. We can add our equals, I guess, if we want. I'm not gonna. And we could add other stuff to it as well, to our stack class, but we gotta be careful not to break the definition of our stack. So, of course, we're gonna wanna test this thing. So here's what I'm gonna do. I'm gonna go here. I've got my stack here. I'm gonna go here. I'm gonna have to include ArrayIntStack. Yep, that's what we need. And then down here, I'm just gonna put this. Okay. So this is a quick check for creating. So I'm gonna build this, and what I should see is I'm creating a pointer to an ArrayIntStack of size 5, and there should be nothing in there, right? We should see like a string of like that just says top of nothing, and then size should be 0 and isEmpty should be true. Let's see if I'm crazy or right. So top is literally nothing, the size is 0, and isEmpty is true, 1 is true. Okay, cool. So we know it works so far, but we only tested a couple of the functions. So let's carry on. Let's try pushing a bunch of things. So we're gonna try pushing, and you'll notice that I only push 1, 2, 3, 4, 5 things here. And these things are dynamically allocated integers. So I better, like when I delete this stuff, I better be sure to delete these things properly. So I'm putting 5 things in here, and you'll see like I made the array size 5. So if I were to come and add an additional thing, we know expand capacity is gonna have to run. But with running this code, I'm effectively not checking or ever going to run expand capacity at this point. Okay, so we create it, toString, blah, blah, blah. We push 5 things onto it, we print it out, the size is empty. So let's see what happens now. Let's build it. Uh-oh, what did I do? Oh, I probably didn't close it properly or something. There, it's happy now. Okay, so what do we see? We see nothing, 0, 1. Yeah, it's the same. Now we see 0, 1, 2, 3, 4, and the top is like the 4. 5 is true, is 0, false. Okay, is true, is empty. Okay, cool. All right, let's go here. Now let's add a couple more things. And this will let us know if expand capacity is working just fine. And by the way, like I'm not just showing you this for my sake of like how I'm testing this code. I'm showing you because you're gonna write code and you're gonna have to make sure that your code works. So I'm just showing you an example of how I could test my stack, and you can test your stack with effectively the same code, but I'm just showing you an example of how I'm testing things and how thorough I'm being. So I'm gonna add a whole bunch of new things, 10, 11, 12, 13, 14. It'll let me know if expand capacity is working just fine. So looks like it is. 0, 1, 2, 3, 4, 5, 10, 11, 12, 13, 14. That's the top, 10, 0. Good. Good stuff. So far so good. Now let's check peak. You might remember peak will give me, it'll return, so when I call peak here, it's returning a pointer to the integer at the top, but it leaves it there. And then I'm immediately dereferencing it and printing it out. Then I'm gonna get the toString size and isEmpty. So we should see that 14 printed out, but the 14, when we call the toString, the 14 should still be on our stack. Perfect. So the 14, yes, this is the peak working. We print it out, we see the 14 still there. There's still 10 things there. It's still not empty. All right, now, oh, we just checked peak. Checking popped, okay. So there's a lot going on here. Now, I'm gonna start with an integer pointer called wasPopped and have it start by pointing to null pointer. Remember, this is the super special value that C++ has that means I'm pointing to nothing. So we can check like, hey, are you equal to null pointer? And then I would know that that pointer is pointing to nothing. So here's what I'm gonna do. I'm gonna create the integer pointer wasPopped, set it to nothing. Then I'm immediately gonna say, okay, wasPopped is pop. So this is gonna give me the integer pointer that was at the top, and the stack should be have one less thing in it. And I'm gonna print it out, and then I'm gonna delete wasPopped, the thing that wasPopped pointed to. I'm gonna do it again. I'm gonna do it again. Then I'm gonna, and then do it 2 more times, except I'm not even printing it out anymore. So I'm doing it 1, 2, 3, 4, 5. So I'm going to pop 5 times. I'm gonna print the first 3 out as I do it. I'm not gonna print the next 2. And then I'm gonna do this right here. And if we did this properly, we should see the 10, 11, 12, 13, 14 missing. They should be gone because they're removed from the stack, and the size should now be 5. By the way, all this code is on Moodle already. So, okay, here we go. So we see the 14, whatever, okay. Size 10, 0. So we pop the 14 and print it out. Pop the 13, print it out. Pop the 12, print it out. We pop out the 11 and 10, but we don't print them out. And then we say, okay, what's this? Like, do the toString on the stack, and there we go. Look at that. It's size 5, and it's not empty. Okay. And I was being very careful to delete all the things as I was removing them from the stack. And let's do it 5 more times, just to see that it's happy with getting rid of everything. You'll see here, I'm not printing them out. I'm just immediately doing another toString. Is it gonna run? Yeah. So there we go, 5, 0. We deleted the 5 last things. Top is there. It's now empty. There's 1 thing in it. So now the last couple things we need to do is test our exceptions. Basically, what happens if I try to pop or peek when there's nothing there? So here's how I do it. I'm going to try to pop it and then delete the thing that I get. But if the exception is thrown, it's going to say I can't do that. And this e.what might only work on the Windows, so you can delete this if you're on Mac. Or if you peek and there's nothing there, and there's an exception, we're gonna print this out. I'm not gonna halt the program, I'm just gonna say like, oh, user, by the way, there's an issue here. If we tried to pop and an exception wasn't thrown, well, we ignore this. This is kind of like an if-else for exceptions. Try catch. Yeah, this is exception stuff. We're going to talk about exceptions more in the class later, I think. But this was a big topic in 161. So it's like what I was just saying though. It's like an if else. Try to do this. If it ran and nothing weird happened, great. It just carries on, it skips the catch and carries on. Same with here. If it tries to peek and nothing funny happens, it just skips the catch and carries on, like the if statement. But if this is called and it throws that exception, we go back here, we do our pop, and if it's empty and we were trying to pop, we're gonna throw this exception, and then we tried it, and if it threw that exception, we're gonna catch that exception, and then this is like, in here, this is where I write the code that says like, well, what are you gonna do about it? And all I'm gonna do is just print out the string, got an exception when trying to pop. And then for peek, got an exception when trying to peek. That's all. There we go, we got 2 exceptions. There we go. Why? Well, because the stack was empty. What is the advantage of try catch versus if else? Well, the exception, I mean, there's a lot. Let me have a look at the slides to make sure I actually have something on exceptions. I'm not sure if I do. All right, everybody. For those of you that do not know exceptions, you've got homework. And I'll just jump down to the exceptions bit. There we go. Of course, this is written for the purpose of Python, but I mean, the idea of exceptions is entirely programming language independent. So there you go. You can learn all about exceptions right there in that link. All right. So, I mean, at any given time, what keeps track of how many elements are in the stack? Well, top. But it also keeps track of where the next available spot is, right? And where does the stack grow and shrink from? Well, the one side, that's, you know, we use top to make sense of. And can our stack ever be full? Well, the way we've written it, no, because we're always going to be capable of expanding capacity. Now, I realize our computers have a finite amount of RAM, but in principle, it could go on forever. And how would our implementation need to change if we had the top be 0? So this is an interesting question. What if we always wanted the top to be 0? We are out of time, so maybe we will come back and talk about this right at the very beginning of class on Friday. Anyways, hopefully you learned something. See you later.